Welcome to the Deep Dive. Today, we're tackling a challenge that's really fundamental if we want large language models to keep up. I mean, how do you effectively update them after they've been trained? Think about it. The world changes constantly, right? Facts evolve. LLMs capture knowledge, sure, but it's from a specific point in time. It gets outdated. Or sometimes you just need to correct a mistake, add something new. Doing that efficiently and crucially without breaking everything else the model already knows. That's the huge puzzle we're digging into. So we're diving into this fascinating new research paper. It introduces a framework called Memoir. It's designed specifically for this problem of lifelong model editing. Our mission today: really unpack why this is so tricky, explore the core ideas, some are really clever behind Memoir, and then see how well it actually performs when you put it to the test. Get ready to shortcut your way to understanding something pretty cutting edge.
That's right. Large language models, LLMs, they're incredibly powerful because they learn from these vast data sets. But like you said, that training captures knowledge up to a certain point. It's static. And the real world, anything but static. New facts emerge all the time. Politics change, science advances, and sometimes, the original data itself might have errors or biases that we need to fix later on. Now, the obvious first thought might be, well, just fine-tune the whole model on the new information. But that's incredibly expensive computationally speaking, takes huge resources, and maybe even worse, it often leads to what researchers call catastrophic forgetting.
Catastrophic forgetting. Sounds bad.
It is. The model might learn the new fact, okay, but it can easily overwrite or just forget things it knew before, including things it learned from previous updates. It's like trying to edit a complex tapestry by reweaving large sections. You risk unraveling the whole thing. And that's exactly why this field of lifelong model editing is so important. The goal is continuous, efficient, precise updates.
Okay, so the goal is clear. Update the model over time with new facts or corrections, a stream of them, potentially. But what makes an edit good? Because it sounds like just throwing new info in can cause all sorts of problems. The paper highlights three key things, right? First, reliability. This sounds straightforward, but it's non-negotiable. If you edit the model, say, correct a fact about a capital city, the model absolutely must give that correct, updated answer when asked that specific question.
Exactly. It has to stick.
Second, generalization. It's not really enough if it only works for the exact phrase you use to make the edit. A good edit should generalize. If you tell it Paris is the capital of France, it should also know that when asked what's France's capital or the capital city of France is, same fact, different words.
Right. It needs to understand the underlying concept.
And third, and this sounds like the really tricky one, locality. The edit should only change the specific piece of knowledge it's supposed to. Updating France's capital shouldn't make it forget Germany's capital, right? Or start talking nonsense about physics. And critically, it shouldn't mess up edits you made before.
Precisely. Balancing these three, reliability, generalization, and locality, that's the core tension, that's the challenge. Many existing methods. Well, they often struggle with this balance, especially as you pile on more and more edits over the model's lifetime. Some might be reliable and local for a while, but they just don't generalize well. The knowledge is too narrow. Others might generalize better initially, but they quickly start forgetting older edits as new ones come in. Reliability drops, locality breaks down, gets messy.
So that brings us to Memoir. How does it try to nail this balancing act? Especially tackling that forgetting problem when you have lots of updates.
Okay, so this is where Memoir takes a really different path. It's quite elegant, actually. Instead of trying to directly modify the original model's weights, which are these billions of parameters, incredibly complex and interconnected.
Like brain surgery, you said.
Exactly. Like trying to perform super delicate surgery on a massive scale, every single time you want to add one fact. It's risky and hard to control, Memoir says. Let's not touch the original model. Leave those pre-trained parameters frozen. Instead, it adds what they call a residual memory module.
Residual memory.
Yeah, think of it like adding a dedicated brand new notebook alongside the model's original huge library of knowledge. This notebook starts empty, or zero initialized, as they say. All the new edits, all the new facts or corrections, they get written into this separate notebook, this residual memory. The original library stays untouched. The model's final output then becomes a combination of what it reads from its original library and what it finds in this new memory notebook.
Okay, I like the notebook analogy. It keeps the original safe. But if you keep writing all the new edits into the same notebook, page after page, won't you eventually run into the same problem? New notes potentially overwriting or messing up older notes within that memory module? It sounds like forgetting could just happen there instead.
That's a really sharp question. And it gets right to the heart of Memoir's second key idea. This is where they use a technique inspired by continual learning specifically, sparsity.
Sparsity, meaning it only uses a small part.
Exactly. For each specific edit, say, correcting one particular fact, Memoir doesn't update the entire residual memory module, not the whole notebook. Instead, it dynamically selects and updates only a very small, specific subset of the parameters within that memory module just for that single piece of information.
Ah, okay, so it's not writing on the whole page, just a tiny corner.
Kind of. Imagine the notebook has, like, thousands of tiny numbered slots or locations. When you make a new edit, Memoir figures out a very specific, small set of those slots to write that particular piece of information into, all the other slots, left completely untouched for that edit.
Right, selective writing. But how does it decide which slots? Is it random? Or is there a smart way to pick the location for each note so they don't clash?
Not random, no. This is where their mechanism called top hash comes into play. It's pretty clever. Top hash is basically the system that generates what they call sample-dependent masks. Think of a mask like a stencil, or maybe a unique key for each input.
A key?
Yeah, a key that tells the system which memory slots are unlocked or accessible for this specific piece of information being edited. When the input prompt for an edit comes in, Top Hash looks at the model's internal reaction to that prompt, what patterns or features it activates strongly. It identifies the most important features, the top K strongest activations, usually related to the last word, which often summarizes the input.
Okay, so it finds the input's main fingerprint.
Pretty much, and it initially selects the memory slots linked to those top features. This
Right.
makes sense, right? Similar questions should activate similar features, so they'll point towards a similar set of slots.
But wait, if very similar questions always point to the exact same slots, wouldn't that still cause overwriting eventually?
Yeah, spot on. That's the potential problem with just using the top features directly. So Top Hash adds a crucial second step. It applies a fixed random permutation, a shuffling, to those selected top K indices.
A fixed shuffle, meaning it's random, but the same random shuffle every time.
Exactly. It's determined once for the model and then stays constant. So here's the clever part. Semantically similar inputs will still identify a similar set of important features, the initial top K. But this fixed permutation then maps those similar feature sets onto different distributions of actual parameter columns or slots in the residual memory.
Ah, so the shuffle scatters them differently, even if the starting point was similar.
Precisely. It introduces this necessary diversity. Each edit gets stored in its own unique sparse pattern of locations within the memory. It minimizes the chance that a new edit will accidentally land on the exact same slots used by an old edit.
Okay, wow, that's quite intricate. So you find the topics, but then use a secret code to scatter the notes into very specific spread out locations. That separation is key to stopping them from interfering with each other.
You got it. That strategic, sparse allocation within the residual memory is fundamental. It's what helps Memoir fight off catastrophic forgetting, especially when you're talking about not just tens, but hundreds or even thousands of edits over time. Okay, so that's how edits get stored without messing each other up too much. But then there's inference time. A user asks the model a question after maybe thousands of edits have been made. How does Memoir efficiently figure out, is this question related to something I've been edited on? If yes, which specific edit? And how do I retrieve just that piece of information?
Right. It needs to know when to check the new notebook and which page to turn to versus just sticking with the original library.
Yeah.
How does it make that call?
It cleverly reuses the masks generated by Top Hash during the editing phase. Remember those unique keys or fingerprints for each edit? Memoir builds a database, basically a list, containing the mask for every single edit it has processed.
Okay, a mask database.
Yep. When a new query comes in from a user, the model generates a mask for that query, using the exact same top hash mechanism, top hash features plus the fixed permutation. Then it compares this new query mask against all the masks stored in its database of past edits.
How does it compare them?
It uses a simple measure, like Hamming distance, essentially calculating how similar the patterns are, how much the new query's mask overlaps with each of the stored edit masks. It finds the closest match.
Finds the edit mask that looks most like the current questions mask?
Oh, exactly. And based on how much they overlap, they called it the overlapping ratio, Memoir makes a decision using a preset threshold. If the overlap is high, above the threshold, that means the new query is semantically very similar to one of the prompts that was edited, or maybe it's the exact same prompt. In this case, Memoir says, aha, this is relevant to an edit. It then activates the residual memory module. And crucially, it applies the mask of the closest matching edited prompt to the memory's input. This acts like the key to unlock and retrieve only the specific information stored in those particular scattered slots for that relevant edit.
And if the overlap is low?
If the overlap is below the threshold, Memoir concludes the query is unrelated to any of the specific facts it was edited on. In that situation, the residual memory module is completely deactivated for this query. It stays silent. The model then relies solely on its original, pre-trained knowledge, the big library, to answer the question.
That conditional activation, that sounds really powerful.
Yeah.
It only brings in the edited knowledge when it's confident it's relevant based on that mask similarity. So for totally unrelated questions, the memory module just sits there, not interfering.
Exactly. It preserves the model's general knowledge and prevents the edits from bleeding into irrelevant contexts.
And the paper mentioned this approach avoids needing huge data sets of negative examples during training, right? Like explicitly telling the model all the things it shouldn't change.
Correct. Some other methods require that, which can be laborious to create. Memoir's conditional activation based on mask matching handles locality much more elegantly during inference. So naturally, the researchers put Memoir through its paces to see if all this theory actually holds up. They ran extensive experiments using standard benchmarks, testing it on different popular LLMs, Llama 3, Mistral, GPT-J. They tested things like question answering where facts change, correcting factual errors or hallucinations the model might make, and checking generalization to rephrase questions. And all the while, they measured locality. Did it mess up other stuff?
And the verdict. Did the separate memory, the sparse updates via top hash, and the conditional activation actually deliver?
The results reported in the paper are genuinely quite impressive, especially, and this is key, as the number of edits grows large. On question answering, for instance, Memoir consistently showed the best balance across those three crucial metrics: reliability, generalization, and locality. Other methods often showed a trade-off. Maybe they stayed reliable, but generalization dropped, or vice versa, especially after hundreds of edits. Memoir seemed to maintain high scores across the board much better.
And they really pushed the number of edits, didn't they? I saw numbers like 1,000, 5,000, even 7,000 edits mentioned.
Yes, and that's where Memoir really shone, highlighting its scalability. This is often the breaking point for other techniques. Many existing methods just, well, their performance collapses when you try to make thousands of sequential edits. They suffer badly from catastrophic forgetting, messing up earlier edits, or unrelated knowledge. Memoir, in contrast, maintained a high average performance across all metrics, even at 5,000 or 7,000 edits on Llama 3. They showed results where, at 5,000 edits, Memoir had an average score around 0.93 across the board. The next best method they compared against, Grace, was down at 0.77, and notably, Grace struggled significantly with generalization at that scale.
Wow, 0.93 average. Reliability, generalization, and locality all holding up after 5,000 distinct edits. That seems like a pretty dramatic demonstration of resisting forgetting.
It really is. The paper includes analyses showing that Memoir caused minimal performance degradation on the earlier edits in the sequence, much less than the baseline methods. That's direct evidence that its mechanisms, the sparsity, the conditional activation, are working as intended to mitigate forgetting. They also did ablation studies testing the system with parts removed, which confirmed that both the conditional activation step at inference and the specific top hash strategy with the fixed permutation were critical components for achieving this level of performance and scalability. Take one away, and the results weren't nearly as good.
Okay, so stepping back from the technical details, the residual memory of the top hash masks, why should you, our listener, care about this? Well, because this kind of research directly impacts how reliable, how trustworthy, and ultimately how useful the AI tools you interact with can become. Imagine using an AI for something critical, maybe summarizing medical notes, providing technical support, getting legal information, or even just getting accurate, up-to-the-minute news. You need that information to be factual and current. You can't have it hallucinating old data or giving you dangerous misinformation. Model editing techniques like Memoir are the engine that could allow developers to deploy a powerful AI and then continuously refine it. They can inject new safety guidelines, correct biases they discover, patch factual errors, add the latest research findings after the model is already out there.
Exactly. Think about it. A framework that can handle potentially thousands, maybe tens of thousands, of updates reliably over time. Learning new things, correcting mistakes, but crucially, without forgetting previous corrections or damaging its vast store of general knowledge. That means LLMs could potentially evolve almost in real time alongside the real world. This could lead to significantly more trustworthy AI, dynamically accurate AI that you can actually rely on in rapidly changing fields like medicine, finance, or current events. It's a really fundamental step towards building AI that maintains its integrity and usefulness throughout its entire lifespan. Now, the paper is good about acknowledging limitations too. It's not a magic bullet for everything yet. For instance, their current implementation of Memoir focuses on inserting this residual memory into just one specific layer within the transformer architecture.
Okay, just one layer.
Right. And while that seems very effective for the kinds of factual recall and correction tasks they tested, they note that extending it to modify multiple layers might be needed for more complex kinds of knowledge or edits that require broader changes in how the model processes information. That's future work.
Makes sense.
Also, their experiments were primarily on decoder-only models like the GPT family, Llama, Mistral models, really good at generating text. How well Memoir works on other architectures, say multimodal models that handle images and text, or encoder-decoder models often used for translation, that's still an open question for future research.
So we've taken a pretty deep dive into Memoir today. It's a really fascinating approach to a critical problem for LLMs. By using that dedicated residual memory, keeping the original model untouched, and then using smart sparse updates via top hash with that clever permutation trick. And finally, the conditional activation during inference based on mask similarity. It manages to inject new knowledge effectively, precisely, while doing a remarkably good job at minimizing that dreaded catastrophic forgetting and maintaining locality, even scaling up to thousands of edits. This ability to continually update models reliably, letting them learn new facts, fix errors without breaking what they already know that, really does feel like a significant step. It's moving towards AI systems that can keep pace with our world and stay trustworthy over time.
Indeed it is, and it leaves us, and you, with a pretty interesting thought to chew on. As AI gains this capability, the ability to continuously learn, adapt, self-correct with this kind of precision, using methods like Memoir, how might that fundamentally change how we use, and importantly, how we trust intelligent systems, especially in really dynamic situations where information is constantly changing? What new applications suddenly become feasible when AI can seamlessly absorb and integrate the ongoing flow of new information the world throws at it?